let's look at a few examples of using the comparison test to tell if series diverge or converge. One tricky thing about using the comparison test is that there's nothing to tell you what to compare your series to. This can be kind of tricky, right? What we'll see is that what we will compare our series to are geometric series, the harmonic series, and p-series. Those are the typical series to compare our series to, because we know whether each of these converge or diverge, right? So these are the useful series to compare to. All right, so let's check on this one. Let's see if the sum from n equals 3 to infinity of 2 over n times n plus 1, if that converges or diverges. So that isn't a harmonic series or a geometric or a p-series. It's a little hard to know what to compare it to. One thing you might do is you might ask, well, what happens if we multiply out the denominator? That would give us 2 over n squared plus n. And that's not a p-series, but if you kind of squint so that you don't notice the plus n, it almost looks like a p-series, right? It looks like 2 times 1 over n squared. And this, right, we know that the series 2 times 1 over n squared, that's the same as 2 times the sum of 1 over n squared. And this is a p-series, right? So let's see if, and in particular, it's a p-series that converges, because it's a p-series where p is bigger than 1. So let's see if we can make this, make the comparison work out. So if we're going to compare to 2 times 1 over n squared and hope to find that this converges, we need our terms, 2 over n squared plus n. We need to convince ourselves that these are between 0 and 2 times 1 over n squared. So these terms are definitely bigger than 0 because they're all positive. But why is it that our terms, 2 over n squared plus n, why is it that that's less than or equal to 2 times 1 over n squared? 2 times 1 over n squared is 2 over n squared. So why is it that 2 over n squared plus n is less than 2 over n squared? Well, the reason is because 2 over n squared plus n has a larger denominator, right? So when the denominator of a fraction is larger, the fraction itself is smaller, and so 2 over n squared plus n is less than 2 over n squared. We already know that the sum of 2 over n squared converges, right? We figured that out before. It's twice a p-series. So the comparison test tells us that the sum from n equals 3 to infinity of 2 over n squared plus n also converges. All right. Next up, let's decide if this weird-looking series converges or diverges. We need to decide what to compare it to. It's hard to know because of the sign right here, but the numbers we're putting into this sine function are always positive, and also they're always less than 1. Right? 1 over n as n goes to infinity, that's always less than 1. So the numbers we're putting into sine are between 0 and 1, and that means that this number up here is always positive, right? On the interval from 0 to 1, sine is always positive, right? Sine looks like this. Sine doesn't go negative until you get past pi, and our inputs never get that big. So this numerator is always positive. Our denominator is also always positive, clearly. So what are we going to compare this to? Right? We need to compare sine of 1 over n over square root of n cubed, we need to compare that to something that we know the convergence of. Well, the denominator here is a power of n, so maybe we should compare this to a p-series again, right? P-series are extremely useful for the comparison test. But what about sine? Well, right, for the comparison test, we need to find a series bigger than or equal to the terms that we have. And how big does sine get? Well, sine never gets bigger than 1, right? So if we put a 1 right here and a square root of n cubed in the denominator, right? 1 over square root n cubed is definitely greater than or equal to sine of 1 over n over square root of n cubed, right? So we have our comparison. Notice that this 1 over square root of n cubed, this is actually 1 over n to the 3 halves. So the sum of 1 over n to the 3 halves from n equals 1 to infinity, this is a p-series, and p is bigger than 1, right? So this converges. But that means that the series we started with also converges by the comparison test, right? We have a series of positive terms, a bigger series converges, and so our series must converge as well. Okay, let's look at this one. How about this series? Sum from 1 to infinity of 1 over square root of n plus 1. So, first of all these terms are positive, right? So what to compare it to? You might try comparing it to 1 over square root of n, right? That seems good, because that's a p-series. 1 over the square root of n is bigger than 1 over square root of n plus 1, because the denominator is smaller, right? The fraction with the smaller denominator is the bigger fraction. A smaller denominator makes the fraction bigger. Okay? So we're comparing 1 over square root of n plus 1 to 1 over square root of n. So what is the convergence of 1 over the square root of n? Well, this is a p-series with p equals a half, because of the square root, and that's less than 1, and so this diverges. Okay, so our series is smaller than a divergent series, but wait, that's backwards. We can't draw any conclusion from that, right? To use the comparison test, you either need to compare to a larger convergent series or a smaller divergent series. But we sort of crossed the streams and we compared to a larger divergent series, and that's not helpful, right? So this actually didn't help. This was not the right comparison to make. If we think, like, my intuition is that this series that we have is very similar to 1 over square root of n, so probably it diverges, but this comparison doesn't actually show that it diverges. So if we think it diverges, we should compare it to a smaller series that diverges, right? Because that's the comparison test says if you compare to a smaller series that diverges, your original series diverges. So we should figure out a smaller series that diverges. And it's not totally obvious what to do. This is one of the tricks of the comparison test, is figuring out an appropriate series to compare it to. And what you could compare this to, so again, we need to make the denominator bigger so that the fraction is smaller. And what we can do is we can make the denominator bigger by replacing this 1 with the square root of n, right? Because when n is bigger than or equal to 1, because our series starts at 1, so this square root of n is bigger than or equal to 1, right? So we're making the denominator bigger, and that makes the fraction smaller. Okay. All right. But now we need to check, okay, does the sum of 1 over square root of n plus square root of n, does that converge or diverge? Well, let's simplify this. This is the sum of 1 over 2 square root n. But that's, right, we can slide this 1/2 out front. This is 1/2 times the sum of 1 over square root of n. But the sum of 1 over square root of n, this is a p-series. Right, that's the p-series we were hoping to use before. This is a p-series with p less than 1, so this diverges. All right. So finally, we've compared our series to a smaller series, and the smaller series diverges. So the conclusion we can draw from the comparison test is that our series, the sum of 1 over square root of n plus 1, this also diverges. So the moral of the story on this example is you have to be careful about whether you're making your terms bigger or smaller. If you compare to a bigger series, you're hoping for convergence. If you compare to a smaller series, you're hoping for divergence.